Calculus BC, Lesson 6.1, Estimating with Finite Sums. So this changes everything. We started off in differential calculus, looking at the instantaneous slope of a curve, tangent line of a curve at a point. Now we're working on the other half of calculus, the integral calculus. And we're going to combine these two, and it's going to take us a while to do it. Most people get this question here about the train at 75 miles an hour, and they say, oh, that's easy, distance equals rate times time. It's going at 75 miles an hour for 2 hours, and I'm skipping out on the units, that's 150. Another way to do it is to say it's going at 75 miles per hour from 7 to 9. That's the speed it's going at. And we're looking at the area of the rectangle under the curves, so to speak. So that's integral calculus right there. Seems like a really innocuous idea, but most of the calculus we do starts off pretty low key, and we just usually label it from A to B, and the function's, doing its thing. Try and line that up a little bit better. So it's not constant. How do we find the area under the curve? Well, that's the integral. We'll get there. It's going to take us a little while to build up to it. But here's an example. A particle starts at x equals 0 and moves along the x-axis with velocity v of t equals t squared. So our a is 0. Then it gets out here to 3. And call that 9 up here. Does something like that. And the question is, what's the area under the curve? Well, we don't know. We've got all sorts of little techniques we're going to use, but the typical way to do this is to build rectangles, and we're going to keep it short and sweet, 1, 2, and 3. And we're going to build what we call MRAM. We're going to go to the midpoint. I'm going to change up colors here. And we use these rectangles to kind of approximate the area under the curve. You see, it's somewhat poor, but not that poor, because this chunk of rectangle go here, and this chunk of rectangle go here, and this chunk can almost go here. So it gives us a way to approximate it. And it's a pretty cool, dare I say, slick technique. I have gone on the Desmos website, and yeah, I need to make it a little smaller. This thing's giving me a hard time. Got it. Nope, don't got it. Still don't got it. Alright, got it. So, hard to see. Now you have to make it big and just play with it and pray that it works out. Nope, hates my guts. So I have a little trouble with the window screen here, but we'll get the idea. So this is an MRAM demonstration. And you can see it's hitting at the midpoints here, all the way up the curve. And it calculates the area over here as 2.66. And you can, I'm not going to do the calculations, but you can easily say, oh, it's just a bunch of rectangles. And the point of what I'm making is that we can make those divisions significantly more, and then more, and then more, so that they become more and more accurate. We can do it on the left side, where the left side hits, and just more and more until they become accurate. We can do it on the right side, where the right side hits. As you can see, MRAM will be much more accurate because it splits the difference, but all of them are going to work if we make the divisions we use infinitely small. There are calculator functions. Page, please. Page, please. and leave page please. There are calculators that will do all this math for you, but today we'll do a lot of the math ourselves. So actually, what the heck, let's do it here. Midpoint 0.5 of x squared, so we get 0.5 squared is our height, and our width is 1, plus 1.5 squared times 1 plus 2.5 squared times 1. And what does that equal? I've got a calculator here. 0.5 squared plus 1.5 squared plus 2.5 squared. Get 8.75. If you looked on the Desmos thing, it said something like 2 point something and change. So I'm not sure what I did wrong. So I will not screw around. This is later in the video, but I'll show it to you now. And this one doesn't want to cooperate. There we go, finally. Something cooperates. Plug in x squared. Oh, actually, I do get a different answer. They were using a different range. Their a and b values are different. X squared. And then I graph it, and I'll pick the window. It's going to go from just off screen, -1 to 5. And I'll do a y min of -1 again, just off screen. And if we're going up to 3, the highest it'll get is 9, so 10 is actually good. Let's graph it. And then we get to use the integral button, which we haven't even gotten to yet, but I'm getting way ahead of myself. I say take it from 0, please, to 3, please. And there it fills it in. And it says it's 9. And we got 8.75. So you can see with just 3 rectangles, we're starting to get pretty close. So, like I said, we just did an MRAM, a LRAM. Looks something like this. Where it comes up and hits. This one's actually a 0. Alright, and you'll say, why would you ever use that? Why not just use the MRAM? It's so much better. And I say, I agree. But you never know, you might get into a domain issue where one works and the other one doesn't. And this is just what calculus teachers do. Don't forget they're evil. Got to keep that in mind. So this would be a RRAM. So it goes here, here, and here. You can see it's going to be too big. But again, as the divisions get smaller and smaller and smaller, it gets closer and closer. So when I tell you to do one of these, I've got to tell you the method, and I have to tell you the number of divisions. Actually, we use a different word for that. We call it partitions. So, find the area under this curve on the interval 0, 3. I'm not going to do it. I'm going to see what it looks like on the calculator. X squared sine of x, I believe I used. Graph it. Alright. So it looks something like this. Something like this. So I would always do an MRAM if nobody tells me what else to do. And in this case, we're going to go with 3 again. And we'll use that to approximate the area. Use your calculator to check, but it would be something like put in 0.5, so 0.5 squared sine of 0.5 times 1. Now I'm writing in the 1 just to remember you're finding the area of a rectangle, plus 1.5 squared sine of 1.5, 1 plus 2.5 squared sine of 2.5 times 1. And get your area, which again I'm not going to do. You can do this. So next question is, can we do it on a three-dimensional shape? And yes, but this is probably a little bit beyond my capabilities of drawing. Whew, deep breath, here we go. So we could take a sphere and divvy it up into cylinders like this. And the next one would be up here. It won't be that big. Let me change colors. Change colors again. So we are taking a sphere and we're slicing it, and we're making discs, also known as cylinders. We can do the exact same thing here and take a volume of a sphere with radius 4, and I'm just going to get a cross section. The cross section is y equals square root 16 minus x squared, which would actually be plus or minus, but we're just going to do the top side. And if we look at the cross section, we're doing something like this. Keeps going. And then we're drawing in 1, 2, 3, 4. Leave those out for a second. And then we draw an MRAM disc. Alright, so each one of these is a disc in cross section. So to find the area, we're going to add up these discs and multiply by 2. The disc goes all the way down to the other side, but I just cut it off because I didn't feel like drawing it all. So let's find the area of 1, 2, 3, 4. Area of a cylinder is pi r squared h. I made h equal to 1, so I'm not going to draw it in. And r covers the whole thing. Some people say, oh, you're just doing the top half. Remember, that's a whole cylinder. You just need the radius. So we're over here with pi times 16 minus 0.5 squared squared plus pi times 16 minus 1.5 squared squared plus pi times 16 minus 2.5 squared squared plus pi root of 16 minus 3.5 squared squared. And the nice thing about this is the squares cancel out, so I just got to go to town, and I'll just keep pi out front. I'm going to put my 2 now so I don't forget it, because we're going to double this whole thing, times pi. So 16 minus 0.5 squared, 15.75, plus 16 minus 1.5 squared, 13.75, plus 16 minus 2.5 squared, 9.75, plus 16 minus 3.5 squared, 3.75. Multiply that out. Times it by 2, times it by pi. And I get 270 0.177 cubic units. If this was a sphere of radius 4, we would go 4/3 times pi 4 to the third, and we would get 268.083 units cubed. Now, I'm not going to lie, I think that's pretty darn cool. We approximate with a bunch of cylinders, kind of cut and fill it in. The more divisions we make, the more accurate it'll be. So, lots of applications of this. The homework's not that hard on this in terms of just getting you used to dividing things into rectangles and multiplying them up. As in all things, it gets trickier, but it's not too bad. So, as always, happy mathing.